Today we are going to discuss next topic, which is continuation of the previous lecture, that is decimation in time, what we have studied in the last lecture. In this lecture we are going to study the next method, which is decimation in frequency FFT algorithm, followed by inverse DFT algorithm, and we will see one problem how this DIF FFT algorithm is going to solve for the longer sequences. Fine. So in these sequences, in this particular lecture, I am going to discuss about the decimation in frequency problem. On one problem I am going to discuss one problem related to this DIF. Similarly, I have taken another problem related to the DIT and IDFT through the FFT algorithm, and one problem related to the IDFT. And the last slide, just I am going to show you the comparison of the two diagrams, which is DIF and IDF. So in the previous lecture where we have discussed about one method, which is nothing but decimation in time FFT algorithm, and today's the same method, the same algorithm which we are going to study, which is nothing but the decimation in frequency. And what the student can do means, at the end of this session the students will be able to effectively illustrate the example. That means they should be able to illustrate the example, and they should be able to draw the butterfly diagram which is related to the decimation in frequency. This should be the learning outcome after discussion of this particular topic, which is decimation in frequency. And we know that this method is nothing but a divide and conquer approach, where we are going to take the sample sequence and we are going to divide that sample sequence. For example, if I take n is equal to 8, first we are going to divide that 8 into 4, then that 4 is going to divide into 2, which is the radix. So after dividing that, we are going to execute the DFT or else IDFT, so that we can solve the longer sequences with the help of these particular algorithms. So let's see what is happening in this particular things. So what it's saying. So in decimation in frequency algorithm, the frequency domain sequence x of k, you please observe this particular parameter, which is x of k. In the previous section we have taken decimation in time DIT, which is x of n. Now we are discussing about the decimation in frequency, which is which we are going to consider capital X of k. So which that particular x of k is going to decimate. In the previous section, where in the decimation in time, we decimated the time sequence, which is x of n, and this is the particular, in this particular topic, that is decimation in frequency, we are going to decimate the frequency domain sequence, which is capital X of k. Similar, the process will be similar, but a small change, small difference, which we will discuss in the later upcoming slides. So what it says, the endpoint time domain sequence is converted to two numbers of n by 2 sequences, then each n by 2 sequences is converted into two numbers of n by 4. So similar. So what we are going to take, first n is equal to 8, we are going to consider, we are dividing this n is equal to 8 into two parts, that is n is equal to 4, and the another one which is n is equal to 4, and later this is going to subdivide into two parts, that is n is equal to 2, n is equal to 2, n is equal to 2, and n is equal to 2. Like this, we are going to decimate all the blocks, that is n is equal to 8 into sub blocks, and finally we are getting that into particular sequence, which will be in the form of n by 4. What? Here the n by 4 is 8 by 4, that is equal to 2. Until we get the last two sequences, we are going to divide this particular blocks. Then this process is continued. When it will be continued? It will be continued up to when we get the n by 2 number of 2-point sequences. See here, 2-point sequences. Until and unless we get 2-point sequences, we are going to subdivide all the main sequences. And finally, here the equation for n by 2-point sequences, n by 4-point sequences, etc. are obtained by decimating the frequency of frequency domain sequence. We are decimating this frequency domain sequence into n by 4 and later n by 2. So this process is said to be a decimation in frequency process. Now, just before going to solve the problems, just we'll see what is going to happen in this decimation frequency in the form of a mathematical expressions. Let me see. To derive the decimation in frequency, if we get a problem to derive that particular problem in decimation in frequency, for example, he has to do the decimation in frequency by using the FFT algorithm for n and a power of 2, we can first divide that given input sequence into x of n. So for example, if we are given n is equal to 8, for n is equal to 8, first what we are going to do, we are going to divide that give input sequence into 8, like that, x of 0, x of 1, so on up to x of 7. So this is the input sequence what they are going to give, and first what we need to do, that we need to divide that into first half and last half. Like this, after dividing, we are going to execute that by using the DFT, and later on we will continue the same process until and unless we will get n is equal to 2 sequences. Okay, fine. Now we will see what is the equation. We know that the DFT of the equation x of k is given as summation n is equal to 0 to n minus 1 x of n wn to the power of nk. What is this wn to the power of nk? It is said to be a twiddle factor. Okay, this wn to the power of n is said to be a twiddle factor or phase factor. We call it as a twiddle factor or phase factor. So by using this particular DFT equation, x of k is equal to summation n is equal to 0 to n minus 1 x of n minus 1 wn to the power of small nk. Fine. Later what we are going to do, we are dividing this particular equation to half part. Here we have seen x of n is equal to total 8 sequences they have given, and what we are going to do, we are dividing that into first half part and last half part. Same, this particular equation, that is DFT, what I am going to do this equation, I am dividing this equation into first half part and second half part. See, from n is equal to 0 to n by 2 minus 1 x of n wn to the power of nk, this is the first half part. Later wn to the power of n power nk summation n is equal to small capital N by 2 to n minus 1 x of n wn to the power of nk. Two parts I have divided. Fine. Now, so to get a clarity about this particular first half part, n is equal to 0 to n by 2 minus 1 x of n wn to the power of nk, and similarly the second half part, where we are going to stop here, first half we have stopped to n by 2 minus 1, and next continuation n is equal to n by 2 to n by 2 minus 1 x of n plus n by 2. Okay, this is the second half part, wn to the power of n plus n by 2 into k. So two half part we have divided. So what happened here? Here I have subdivided, that means I have divided this particular wn to the power of nk into wn to the power of nk by 2. So a to the power of m plus n is equal to a to the power of m into a to the power of n. So like this I have written. See here, wn to the power of nk into wn to the power of n by 2 into k. So this, we know this property, that is wn to the power of n by 2 into k, where we know this, what is wn to the power of k is e to the power of minus j 2 pi by n. So after doing this, according to this property, we can write this particular wn to the power of n by 2 into k as minus 1 into 1 minus 1 to the power of k. According to the third property which we have discussed in the previous lecture, we can write this particular wn to the power of n by 2 into k as minus 1 into minus 1 to the power of k. So after replacing that particular factor, what I am going to get? See here, I have taken the common wn to the power of nk, I have taken the common in the first term, first summation x of n is first term, and in the second summation minus 1 to the power of k into x of n plus n by 2. So two summation, in the two summation I have taken wn to the power of nk as common, and I have written this particular equation. Now here, now decimating this x of k into even and odd indexed samples. So here, now first I am going to decimate this total equation into even and odd sequence. For that I am taking, instead of k is equal to 2k. Why? Because first I am writing for the even indexed samples. So k is equal to 2k means this particular equation is nothing but the even indexed samples. For that I am writing x of 2k is equal to summation n is equal to 0 to n by 2 minus 1 x of n plus this minus 1 to the power of any even part is said, we can get as a positive term. We know that minus 1 to the power of any even power will be a positive. So instead of minus 1, it will be converted into plus symbol. Then x of n plus n by 2 and w, this is according to the symmetry property, that n by 2 can be written as n by 2 into n power k. Fine. So this is the indexed, even indexed samples, and let it be a first equation. Similarly, I am writing this same thing for the odd, that is k is equal, I'm replacing that k instead of k, I'm replacing that with 2k plus 1, which is a odd sample. This is even sample. Now instead of k, I'm replacing that with 2k plus 1, n is equal to 0 to n by 2 minus 1 x of n. So every negative to the power of odd will be a positive term. So in here I'm going to get minus 1, that is minus into x of n plus n by 2. Here instead of small k, what I'm going to write, I'm writing here as wn by 2 n into k plus 2, 2k plus 1. So I'm segregating this. So I can write it as wn by 2 into n, wn by 2, wn to the power of n into w2k into n. So this I can write it as w power nk to the power of n by 2, which is a symmetry property. Same I am writing, it is reflected here. So this, after segregating this particular term, so wn to the power of small n into wn by 2 to the power of capital N. So here with the help of this particular equation, I have divided that equation into two samples, that is even sample and odd sample. Now, so here how we are going to segregate this, we can see here wn to the power of small n into 2k plus 1. I have written in the form of a to the power of m plus n, that is a to the power of m into a to the power of n. So here the same thing you can see. According to the symmetry property, I am replacing that. Now finally what I am going to do, I am considering this even term, that is let g of n is equal to x of n plus x of n plus n by 2, which is a even term, and let the second, this odd term I am representing with h of n. H of n is equal to x of n minus x of n plus n by 2, that is even term with g of n and odd term with the h of n. So I got two equations, which is g of n and which is said to be a even indexed samples, and considering that odd samples with h of n, that is two equations we got here. Now, so with the help of these particular two equations, I can frame the first stage. For example, I am taking n is equal to 8. So with the help of these third and fourth equations, with the help of these third and fourth equations, this one, with the help of these third and fourth equations, I am going to frame the equations. So this is the even equations from k is equal to 0 to 3, and this is the odd equations from k is equal to 0 to 3, substituting k is equal to 0 to 3. Now for example, g of 0 is equal to x of n, that is x of n, x of 0 plus x of n plus n by 2. So after doing this, I am going to get x of 4. If I substitute n is equal to 1, this is the equation. If I substitute n is equal to 2, n is equal to 3. So this is all the equations which is related to the even indexed samples, and this is the all equations when we substitute for n is equal to, small n is equal to 0 to 3, where we are going to get all the equations related to the odd term. And you can see here w8 to the power of 0. Don't forget that this is one of the index term where it has been multiplied with this extra term which is considered, that means which is reflected in the odd term, where you can see even term you don't have any twiddle factor, but coming to the odd terms, odd index sample terms, the twiddle factor is reflected. So same, by substituting all the values of n is equal to 0 to 3 in the even terms and n is equal to 0 to 3 in the odd terms. So these are the final equations for the first stage equations what we are going to do. So with the help of these particular equations, what will be the butterfly diagram? See here, I consider all the equations x of n. So x of n is equal to, how many we have taken here? N is equal to 8 now. So n is equal to 8. I got all the 8 terms. Based on the particular previous equations, expressions, we are going to draw this particular butterfly diagram, and this is the first stage. That means total n is equal to 8. Total n is equal to 8 is subdivided into n by 4. Sorry, n by 2. N by 2 and n by 2. That is 8 by 2, which is equal to 4 DFT. That is 8 by 2, which is equal to 4 DFT. So this is the first stage. Same, this process is repeated for these 4 terms and 4 terms, and this will be reduced to n is equal to n by 4, that is equal to 8 by 4, that is equal to 2. And this is for 2 DFT, and this is for 2 DFT. This is for 2 DFT. Okay, the same expressions what I have discussed in the previous slide will be continued for the second stage and third stage. First stage is completed here, that is 8 is converted into 4, and the next stage this 4 is converted into 2. Like this, total 3 stages will be formed with the help of the same equations will be repeated for the next 2 stages. So this is the first stage butterfly diagram for the DIF expression. And here we need to recall the things we have discussed, which is computation of DFT over FFT. We have seen that number of complex multiplications and complex additions in the DFT, you can see here complex multiplications is n square and complex multiplications is n into n minus 1, where it is in DFT. So basically by using the computation of DIF over DFT, the number of complex multiplication you can see here n by 2 log n base 2, and the number of complex additions required here is n log n base 2. So with these computations we can decrease the number of multiplications and number of additions in DIF when we compared it with the DF. Maximum number of complex additions and multiplications will be decreased. For example, I have taken one structure of this particular butterfly diagram, first stage. So how many multiplications you can see here? You can see here a minus b into w n to the power of 1, that is 1 multiplications we can see here, and 2 additions we are going to see here, that is a plus b is 1, a minus b 1 additions is going to happen, and according to this also 1 multiplication, that is this 1 multiplication is also going to happen. So this is the butterfly diagram for one stage, and how many multiplications and how many additions are happening in the DIF when we consider it with the DFT. So this is the finalized block diagram of the decimation in frequency, where for n is equal to 8. So whatever the sequences you are going to get, in the problem, this is the finalized diagram how you need to draw. First you have to draw this basic structure. See here, the total 8 sequences. First butterfly, you draw all this 1, 2 from the third and 3. Next similarly, upside 1, 2, 3, 4. So you can see the circle here. How many butterflies here? We got 4 butterfly diagram. This is the first stage. After that, these input sequences, after calculating, we will get the next input sequences, new input sequences we are going to get here. Okay. So after getting, we should not consider this one. For the first stage, after getting the input output from the first stage, these will be act as a input sequences for the next stage. Okay. Now similarly, this n is equal to 8 has been converted into 4 and 4. Now here the 4, 1, 2, 1, 2. So the fourth structure, n by 4, that 4 DFT is converting into 2 DFT. 1, 2, 1, 2. Fine. So here after doing the calculations, what happens here? We are going to get the new input sequence in the next stage. After stage 2, we are going to get again the new input sequence. Now these will be act as a input sequence for the next stage. So here you can see the 4 has been divided into 2. Okay. Now here finally what I am going to get? 1 structure, 2 second structure, third structure and fourth structure, fourth butterfly structure. Fine. N is equal to 8, n is equal to 4 and n is equal to 2. So finally we got 2. After getting this 2, there is no way to continue the process, and that will be the end of that particular problem. So after doing all this thing, this we are going to get the x of t, which is the decimation in frequency values. So this is the finalized basic block diagram, which is DIF, and it will be same to all the problems, but what the difference is that the difference will be when you get the sequences, that sequences will be different. Okay. These twiddle factors will also be same in all the structure. W 8 to the power of 0, 8 to the power of 1, 8 to the power of 2, 8 to the power of 3. This is the twiddle factors for the first stage. In the second stage, that will be reduced to W 8 to the power of 0, W 8 to the power of 2. In the second stage, W 8 to the power of 0, W 8 to the power of 2. So this is the second stage. And after converting that, after final stage, only you are going to see W 8 to the power of 0, 8 to the power of 0, W 8 to the power of 0 and W 8 to the power of 0. Fine. I think you got a clarity how we are going to draw this particular DIF frequency for the FFT algorithm. So this is the basic block diagram. We'll see a small problem for n is equal to 4. For n is equal to 4, how we are going to compute this DIF? See here, compute 4-point DFT. That is 4-point DFT means n is equal to 4. He had given of a sequence. So 4-point means 1, 2, 3, 4. 4 sequences they have given. That is x of n is equal to 0, 1, 2, 3 using DIF FFT algorithm. Fine. First of all, what we need to do that, just take the diagram of the DIF. Take the diagram of the DIF. X of 0 is equal to 0, 2, 1, 3. So 0, 2, 1, 3. We'll see that problem. So consider this particular problem for n is equal to 8. That is, compute the 8-point DFT using DIF FFT algorithm. That is, x of n is equal to how many sequences I have given? 8 sequences. 1, 2, 3, 4, 5, 6, 7, 8. So this is the sequences they have given us to compute by using the DIF FFT algorithm. First, we need to keep this in mind. So what is the twiddle factor? What is the equations we need to do for the each and every stage? First, there will be, see here, A and here from plus B. That's it. In the upper butterfly diagram, it will be only A plus B. Now coming to the down, you can see A and here will be minus 1. So okay, A minus, from here it will be B. So A minus B, and don't forget we have one twiddle factor which is the product of that particular term, that is A minus B into Wn to the power of K. So this is the basic for each and every block diagram butterfly. These two equations will be, mathematical calculations will be happen, and you need to keep these particular values in mind where this value will be fixed for each and every problem. Only the difference is that the sequences will be given different. Fine. So W8 to the power of 0 value will be equal to 1. W8 to the power of 1 value will be equal to 0.707 minus J 0.707. W8 to the power of 2 is equal to minus J, and W8 to the power of 0 is equal to minus 0.707 minus J 0.707. So this is the twiddle factor values which it will be fixed for each and every problems. So we will see how we are going to compute this with the help of DIF FFT algorithm. First stage, I told you, after giving the sequences, just write all the sequences. First x of 0, 1, 2, 3, 4, 4, 3, 2, 1. Total 8 sequences they have given. First, to draw the basic diagram, first stage diagram, I told you, here we have given n is equal to 8. Total 8 terms given means, we have dividing that 8 into 4. 1, 2, 3, 4. Just observe the coloring of this particular, where I am starting. First, start from x is equal to 4. That is 1, 2, 3, 4, 5. See here, where I am starting, x, that is x of 4. At the fifth line, I am starting. I have drawn the fifth line, upside, sixth line, seventh line, and eighth line. Okay, four lines. And where should I start? Starting from first line to fifth line, second to sixth, third to seventh, and fourth to eighth. By drawing these 4 connections will happen here. You should be careful here. 4 connections will be happen where a butterfly form will be formed here. So here, don't forget to do this thing also. You need to represent twiddle factor W8 to the power of 0, W8 to the power of 1, W8 to the power of 2, and W8 to the power of 3. So these are the 3 twiddle factors. And previous slide I told you how we are going to calculate these. So this is the term. First is A plus B, and the second in the down part, A minus B into Wn to the power of 8. Okay. So like this we are going to do the calculations. Now first I will see this one. So what is the value I am going to get here? So here first term 1 plus, where this line is coming from? This line is coming from x of 4, that is, let it be a B. So x of 4 is equal to 4. Here it is going from here and So 1 plus 4. So 1 plus 4 is equal to, I got 5. So the up calculation has been completed. Fine. Now, when you consider this one here, same thing, x is equal to, x of 0 is equal to 1 is going from here and here. Now, I got here 1 minus, just be careful while you are drawing this one. This is the minus term, minus 1, minus 1, minus 1, minus 1. So, I got a from the x of 0, then minus, where it is coming from, x of 4. X of 4 is equal to 4. 1 minus 4. Got it? And what is the product for this? Just observe. Go upside. Yeah. W8 to the power of 0 is multiplied for this particular. So, 1 minus 4 into W8 to the power of 0. And you know the value of W8 to the power of 0? It will be equal to 1. So, 1 minus 4, which is equal to minus 3 into 1, that is equal to minus 3. So, first two terms we got completed. Now, similarly, take this. Where it is coming from? First, it is coming from x of 1. X of 1 is equal to 2 plus. And where it is coming from? It is coming from x of 5. Just see here, x of 5. So, what is the value of x of 5? 3. So, 2 plus 3 is equal to 5. Good. Now, if possible, you continue like this only, not a problem. Fine. Now, for this, you see, where it is coming from? It is coming from x of 2 is equal to 3. So, 3 plus, and from where it is? From x of 6. X of 6. What is the value of x of 6? 2. That is 3 plus 2 is equal to 5. So, like this, upper part, all the first upper part will be a plus b, and this remaining next 4 values will be a minus b into wn to the power of 0. So, like this, by calculating, we are going to get the values of 5, 5, 5, 5, 3, minus 7.707, minus j, I. So, this is the first stage of this particular problem. Now, what is the new input sequences? Then now the new input sequences are these 5, 5, 5, 5, 3, and these are the new input sequences. We should not consider this now. So, this has been completed. First stage, we have done the calculation, we have computed, and we got the new input sequences here. Now, with the help of these input sequences, see, I have taken what input here? All new particular new things what we got in the previous slide. So, now I am considering this as input sequences, and now see here, from 4, I am converting from 4 to 2, 1, 2, 1, 2. So, now butterfly diagram you can see here, and fiddle factor it will be only W8 to the power of 0 and W8 to the power of 0, 8 to the power of 2, that is 4 has been divided into 2 and 2. Now, second part, same, down, down, up, up. So, 1, 2, 2 butterfly I got with the trivial factor W8 to the power of 0 and W8 to the power of 2. Same process. First upper part will be a plus b, and next two upper part will be a minus b into W8 to n to the power of small n. Similarly, first two parts will be a plus b, and second two parts will be a minus b into W8 to the power of, that is n to the power of 0. So, previous, by using this particular diagram, Wn to the power of 0, this is a, this is b, minus 1, here a plus b, and here a minus b into Wn to the power of small n. Wn to the power of small n. Sorry. Fine. So, here by doing all these things, again what we are going to get? We are going to get the new output. The output of the second stage will be this one, 10, 10, 0, 0, and this all the things which is the output of the second stage. Now, these 4, this n is equal to 4, now next it will be converted into n is equal to 2, final thing. So, let it be, how it will be happen. See here, the output sequences which will be the output of the second stage will be the input for the next stage, which is third stage, the final stage. That is, here the 2 is converted into 1, first butterfly, 2, 1, 2, same, and the twiddle factor will be only 1, W8 to the power of 0, W8 to the power of 0, W8 to the power of 0, W8 to the power of 0. So, first here it will be a plus b, that is 10, and from here it is 10, which is 30, and for this calculation a minus b into wa to the power of 0. For all this, a plus b, a minus b into wa to the power of 0, like this for all, a plus b, a minus b into wa to the power of 0, same, a plus b, a minus b into wa to the power of 0. So by doing all this calculation, final result, that is capital X of k, will be formed here. So X of k is equal to, and be careful here you need to consider the bit reversal. Here X of 0, X of 1, X of 2, X of 3, X of 4, X of 5, X of 6 and X of 7 is the input sequences we have taken. After doing all these calculations, these will be bit reversed. In the previous lecture I told you X of 0, 0, 1, 2, 3, 4, 5, 6, 7 will be 0, 4, 2, 6, 1, 5, 3 and finally it will be a 7. Bit reversal, I told you it is a bit reversal process. Okay. Now, while doing this, while indicating this particular thing, don't directly tell it as X of 0, don't tell it as X of 0, X of 1 and X of 2. X of 0, if you in a hurry mode, what you are going to write, you will write it as X of 0, X of 1, X of 2, like this, so on. But it is wrong. The actual output is 0, 4, 2, 6, 1, 5, 3, 7. First even part and next odd part. So be careful while you are going to indicate this particular output parameters, and it should be in the form of even and odd. X of 0, X of 4, X of 2, X of 6, 1, 5, 3, 7. So like this, it should be a bit reverse for the input sequence and output sequences. So this is the process how we are going to compute the DIF using FFT algorithm and how we are going to reduce that sequence with the help of this particular process. So this is the finalized base block diagram. So butterfly diagram, what we have studied in the 3 stages, if we directly draw this is a finalized butterfly diagram, and you can see the output and input X of 0, X of 1, 2, 3, 4, 5, 6, 7, 0, 4, 2, 6, 1, 5, 3, 7. So like this, it has been decimation of the frequency has been done here with the help of input sequences X of n. So this is the X of n. After decimating, it will be decimated to X of k. Okay, this is the finalized butterfly diagram for n is equal to 8 using the DIF algorithm. Now, next topic which is important, computation of IDFT through FFT algorithm. So inverse discrete Fourier transform. Inverse discrete Fourier transform through FFT algorithm. Just a small derivation, which is very simple. The IDFT of endpoint sequences X of k is given as, see here, X of n is equal to the scaling factor 1 by n into summation k is equal to 0 to n minus 1 X of k e power j 2 pi by n into n k. Okay, so I can write this as Wn to the power of minus nk by taking the conjugate here. So by taking conjugate on both sides, I got this equation that is equal to 1 by n summation k is equal to 0 to n minus 1 x complex conjugate of X of k Wn to the power of nk. So this is the finalized formula, which is X of n is equal to 1 by n summation k is equal to 0 to n minus 1 x complex conjugate of k. Now if you see here, if you consider this particular equation with the DIF, don't consider this one now. If we write the equation without this 1 by n, it will be in the form of DIF. Okay, so whatever the output I am going to get, I am multiplying that with 1 by n, which that DIF is converted into inverse discrete Fourier transform. Okay, so you can see the same block diagram, DIF diagram and IDFT diagram will be same. See here, the total endpoint, that is n is equal to 8 is converted into n is equal to 4, and this n is equal to 4 is converted into n is equal to 2, and whatever we get the answer here, up to here the process will be same, DIF process. Up to here it will be DIF process. What is the change? Whatever the output I am going to get here, I am multiplying that with 1 by n. For example, if I got here 16 and it is multiplied with, for n is equal to 8, if I got the output here 16, that is 16 into 1 by n, that is 8. 8 ones are 8 twos are. And what will be the output here? 2. In DIF, the output is 16. If it is IDFT, that output will becomes to 2. Okay? That output will becomes to 2. Same process will be same, everything will be same, the diagram will be same. Only the difference is whatever the output I am going to get, that will be multiplied with 1 by n. So this is the simple derivation of the computation of IDFT through FFT. Just I have taken one problem, just small problem, we'll complete it. So I have considered the n is equal to 4 and sequences 32, minus 4, 0, minus 4. So x of 0, x of 1, x of 2, x of 3. 32, minus 4, 0, minus 4 I have written and done the equations, that is a plus b here, that is 32 minus 4. 32 and from here it is minus, it should be from here, sorry. So 32 minus 0. So what is the answer I got? This one. Now second, minus 4, and where it is coming from? Minus 4. So which is minus 8. Now see here, 32 minus 0 into w4 to the power of 0, it will be equal to 1. What I am going to get is 32. And here minus 4, minus of minus plus 4 into w4 to the power of minus 1. So it is 0. So I got the new factors, new output from the first stage, which is first stage, and I got the new input sequences, which it is acting as an input sequence for the next stage. And after doing the equations, I got 24, 40, and here I am going to get some 32. Here also I am going to get 32. So after getting that, 24 divided by 4. See, I am multiplying this with 1 by n. I am multiplying the answer with 1 by 4. I am multiplying this answer with 1 by 4. Why? Because n is equal to 4 now. So I am multiplying this answer with 4. So what is 24 by 4? I got 6. 4 by 40 I got 10. 4 by 32 I got 8. And 4 by 32 I got 8. So this is the finalized output what we are going to get in the IDFT using DIT FFT. Okay, I think you got the answer. The process will be same. Only the thing is that whatever the answer you are going to get in the final stage, that will be multiplied with 1 by 4. So this is the concept of the IDFT and DFT. And finally, I want to show you the comparison of DIT and DIF. DIT and DIF. See here, two structures I have written here, DIT structure and DIF structure. You can see the differences. Here, x of 0, x of 4, see the input what I am going to get in DIT. 0 bit reversal 0426 1537. The first difference is bit reversal. The input how I am writing here, you just see here, x of 0, x of 4, x of 2, x of 6, which is even part and odd part. Okay, even with the help of bit reversal, I have taken the input sequences in the form of even part and half part, and the process see here 2, 4, 8. Okay, and output, you can see the output here. It will be same 0, 1, 2, 3, 4, 5, 6. That is x of n will be in the bit reversal form and x of k will be in the same form. The butterfly reduction decimation, you can see here, it is decimated 2, 4, 8. Now same problem if you do with the help of DIF, you can you can consider the input sequence. I am writing the input sequence 0, 1, 2, 3, 4, 5, 6, 7. Here 8, 4, 2. 8 is divided into 4, 4 is divided into 2, and finally this output is bit reversal. This output is bit reversal. Bit reversal. You can see first 4 even part and next 4 odd part. even, odd. So x of 0, x of 4, 2, 6, 1, 5, 6, 7. Okay. What I am going to say means, if you turn this particular structure to the left hand side, it will be reflected as DIF. That is, I can say here the DIF FFT is the transpose of the DIT FFT. So in the next class, we are going to discuss about the main topics which is very important when we are going to study in the digital signal process, which is nothing but the filters. In these filters, two main filters are going to discuss. One is FIR and IIR. In the next upcoming lecture, we will discuss the total topics which is related to FIR, which is finite impulse response, and it is very important not only for the external exam but also the gate problems. Okay, thank you.